All right, let's go ahead and look at some of the things that might show up on the lab final exam. So most of the questions in this class are recycle. Things that were on quizzes came from discussions. Things that were on lab activities or virtual labs or simulations, again, get cycled back into discussions or some of the pre-lab videos or warm-up videos or end up on quizzes. All of these are sort of cyclical. So the final exam is going to, rehash some of these same questions. I can go ahead and tell you, though, that because I don't give you a formula sheet, I'm not going to require you to know very many direct formulas. I tried to avoid them as much as possible. There are some cases where having known a formula might make a question a little bit easier, but you could still work from a concept and figure it out. So something like converting grams and kilograms and newtons, that's not going to be on there because that requires some direct calculation. Finding spring constants, again, not going to be on there. Something like this might be fair if you know that it's a linear relationship. If you've got half the mass, then you're going to see half the stretch. So, again, that's not a direct formula. You could technically use one, plug one, make that work. But, we're looking more for concepts. So let's see some other things that might be reasonable. Okay, so like for a spring constant, again, there's a formula that shows this, but think about it. A spring constant is how strong a spring is. A higher spring constant means it's stronger, there's more force involved. So if there's a higher spring constant, then it's pushing and pulling and making more forces, and therefore it's pushing and pulling harder. It's going to move things faster. So think about what that might mean for what would happen to the period, the amount of time it takes for the spring to move up and down or side to side. On the other side of things, if we're dealing with a heavier mass on a spring, then we're trying to move something that's heavier. So think about it. If you're trying to carry something that's heavier, it's going to be harder to move around. You're not going to be able to move around as quickly. So it's going to take longer for the spring to cycle, which means the period gets longer. Let's see, try to do a little bit from each section. Okay, well, here's one that would be good. Potential energy, when you've got a swinging pendulum, it goes back and forth and back and forth. Remember that potential energy is going to be the ability to do something, right? Again, there's a formula that you could use, but use physics common sense, think it through. The pendulum has potential energy when it's drawn back to one side. Think about a kid on a swing. Technically, they would be like the form of a pendulum. So their potential energy comes from the fact that they've been drawn back and raised up a little bit. So lowest potential energy, think about where that might be. Kinetic energy. Kinetic energy is related to motion. Again, there's a formula, but you don't necessarily need it. Kinetic means moving, right? So the speed of something. Think about when a kid on a swing or a pendulum would be moving the fastest or the slowest, and then use that to figure out what the kinetic energy would be. All right, let's see. Again, any of these that are asking you to do conversions, don't worry about those. Any of them, calculations, same thing. Okay, here's another one. So remember that voltage is a measure of potential. So thinking about that as like your ability to push around and to make current. And current is the actual like flow of electricity. So think about what resistance would mean, right? Several of these are about resistance. The plain English word resistance means to work against something, right? So if you've got more resistance, if you've got more working against you, think about how that's going to affect your ability to push around current. Similarly, in the next question, when we're trying to find the maximum, or in the next one even, we're trying to find the minimum for current. Think about your potential, your ability to push, versus your resistance for what's working against you. right? And then think about what would be the most favorable or least favorable combinations for something like that. Um, Charges, right? Positive charges and negative charges. Again, you could plug into a formula and you could figure that out. But I think, the old saying about how opposites attract could also kind of put you in the right direction. Think about signs. What kind of an answer do you get when you multiply like signs? A positive with a positive or a negative with a negative? Um, let's find something from the next group. I don't want to do too much in each section, just small hints. Okay, in series. So if we have resistances in series, again, remember resistance is going to be something that works against you, makes something harder to do. So again, harder to make electricity to flow around, to have current. If we have more resistances in series, that means we have them in a row. So if we have some kind of circuit, so right now they have no resistance. If we had one resistance and the number here doesn't matter, then if there was only one, then that's all the resistance we're going to have. But think about it now. If I had several more resistances, then now the electricity has to flow through all of those, one after the other. And think about whether that's going to make that easier or tougher for current to move. Think about what that would do. In parallel, remember you've got branches. So these are probably going to get an even worse drawing from me. So my apologies for my artistic ability or lack thereof. But if we have parallel resistors, then each of these squiggly marks is a resistor. And what's important with this is that you've got different branches and ways that the current can go. So current can skip certain resistors. It can only go through one resistor. It could go through this one instead or that one instead. The current has choices. All right, let's see what else we have. Again, most of these with direct calculations that you're not gonna have to worry about this. In theory, they should still something you should be able to do, but because I'm not giving you a formula sheet, they're excluded. This is something that we talked about over and over again in that section. So remember, the speed of light is, for us, 3 times 10 to the 8 meters per second. Now it's really like 299 million, 792,476 or something like that. I started making numbers up at some point. But this is really, really, really close to the true value. It's like less than 1% off. So think about what this might be in terms of anything else that's here. Also remember, we had this very complicated thing. We had gamma is equal to 1 over big square root of 1 minus v over c squared, and this whole huge terrible thing. But if something is not moving, then that means this part doesn't exist, and technically you have 1 over the square root of 1 is just 1, right? So remember that this relativistic factor is for something that's moving sufficiently close to the speed of light. If it's moving 0 times the speed of light, it's not going anywhere. So there's not going to be an effect. Think about what that would mean. If something's not moving, again, no effect. Think about what that would mean. Something like this. Is there a linear increase? Well, you saw how complicated that formula was again a minute ago. Again, you don't have to memorize that formula, but if it's asking you if it's a linear increase, basically, is it easy? Is it simple? It's certainly not yes. You might think it's quadratic because there's a square in there, but remember there's a square root and a fraction involved, a bunch of weird stuff. It's not really going to be random because there's a formula. So again, you can whittle it down, think it through. It is certainly not linear. Linear would mean that you'd have a straight line. You'd have twice the factor for twice the speed, or half the factor for half the speed. All right, let's find some from the next group. Okay, so for the photoelectric effect, what you want to remember is that wavelength and frequency are inversely related to each other. So that means a smaller wavelength is a higher frequency. So that means it's kind of backwards, but a smaller wavelength is going to have more energy. So think about that here, right? So um, you have more energy from this wavelength of light, so that's going to be the most likely one. It's not just any. That's actually was a big part of the point of the photoelectric effect. This is why that kind of setup eventually won Einstein a Nobel Prize. It does matter for the wavelength. That was the whole separation between the duality, the different kinds of ways you can view light. So smaller wavelength is always going to be more energetic. Okay, so similarly, and in fact, this goes back to what we were talking about before. If we have a negative potential here and a positive potential here, think about that as pushing electrons around more, right? So that's going to make them move faster. The trap here is you might think that the current would increase, but if you view the setup, if you look back at your notes, or if you look at the simulation while you're studying, not during the test, please, then that gap between the setup, um, that's where the electrons are moving through. It's going to make them move faster across that gap, but it's not going to overall um, change the amount of current that you're going to read. Okay, these questions a lot of times trip people up on the quizzes and on some of the lab activities. There's a big difference between being slowly hit by electrons and being bombarded by electrons. If the current or if the electrons are being fired very, very slowly, then it'll potentially raise up energy and then drop back down before the next one hits. But if they're being bombarded, then that means that they're being hit very, very quickly, and the energy of multiple interactions will increase here. So you might have the hydrogen is already in an excited state, gets hit by another electron, gets more energy, and jumps to an even higher state. So bombarded is going to be the most likely. There are some different conditions, so check your notes and your previous work and see why. But if it's bombarded, it's most likely at every possible energy level. Something to keep in mind, see if I can find one. If you are under n equals 2, then that means you never had enough energy to make anything happen. So it doesn't matter. If you're under n equals 2, that's always just a no. You have to be able to get to an excited state before you combine and have multiple excited states. So there's not enough energy. What's a little bit weird is we need to remember that the n equals 1 is ground state. So 1 is the bottom. You know, think about in the United States how we talk about floors in the building. First floor is the bottom. In other countries, they don't do it quite that way. If you're interested, you can look it up and see, but that's getting distracted a little bit. Okay, again, don't worry about direct calculations. It's something I hope you would be able to do. It follows from some of the quizzes and other activities, but not something I want you to have to do for the final. All right, let's find something out of the last little bit. Oh, you know, these are, you can find the Balmer series, Passion series, a Fun series. So if we're talking about hydrogen in particular, it's worth looking up and seeing what kinds of photons you tend to get from the different series. Each of these has a special name. And then for inner shell electrons, that is something special. So keep in mind what I just said. The other ones are combinations of visible, infrared, and ultraviolet. If these are special, what's the remaining choice there? So again, these are super high energy because they're typically going to be larger elements anyway. So this one's actually not going to be typically hydrogen. Hydrogen's not going to have inner shell electrons. This will be something with 50, 60, 70 total electrons or protons. Okay, not going to need to know the names of the specific types of decay here, at least not from that. But what would be useful to know is that if you're dealing with alpha decay, like you don't have to look at this and determine, okay, which one is it? You probably could if you tried to draw it out. But you should know that an alpha particle is a helium-4 nucleus. So remember that that's going to have 2 protons and 2 neutrons. If we're dealing with beta decay, for beta positive, it's not a real particle. So it has a 0 at the top. So beta positive or beta plus changes depending on the source. That's not a whole particle. It's actually pieces of particles. So we start talking about electrons, positrons, and neutrinos and antineutrinos and energy and weird stuff. We're not going to go into that. But just know that there's no full particle. There's pieces of particles. It does cause the transition stuff that's being mentioned here. And then beta minus or beta negative goes in the opposite way. So you do not need a periodic table. You should not use a periodic table. You can estimate or guess what's going to happen with these things. You can make up an element. Let's say we've got element Q, and it's got 10 protons and 20 total nucleons, and then you could use that to kind of figure out what's going to happen in the process like this. But I'm not going to ask you to go backwards and name it like, okay, this thing turns into this thing. What happens? That's also unfortunately subject to being Googled and free answers, and that's not allowed. Okay, one of the last things then, if we talk about a half-life, so this got cut off, but I can just draw it back up here. Remember that means the statistical average amount of time it takes for about half of a material to break down into something else. So be careful with this. Remember, if I've got 100 atoms of a radioactive isotope, after a half-life, there's going to be 50 of them left. After another half-life, it's not going to be 0. That's a common mistake. The students think, okay, half is gone. Now the other half is gone. But it's going to be half from this point. So half of 50 now is 25. And then after that, you're going to have about 12. You can't have a half a particle, and these are slightly random anyway. And then you get down to like 6, 3, 1, and then eventually like nothing. And that's random. So the simulations with the warm-up materials and the stuff that matches those extra videos on YouTube show you some setups like this. Now, you also need to be careful. So this is the starting element. So this is the original substance. And then, so like these are the ones that have not decayed. For the ones that have decayed, for the first little bit, that's not going to be much difference. But remember, we start out with 0 decayed. After half-life, 50 have decayed. Now, be careful with this. This is, again, where students get mixed up sometimes. There's 100 total atoms if we're talking about it this way. After this point, another 25 decay. This bottom part, think about like the total that have broken down. So another 25 are going to break down. That's going to go up to 75. And this is going to be technically like 87 and a half, but you can't do that. So something like 88 and then 94. So remember, if you're looking at what's left, then that number is going to keep going down. If you're looking at the ones that have broken down, that number is going to keep going up. But they should always add to 100. So that's something that's a very common mistake. That actually handles like several of these questions through here. And then, like I said before, know the different kinds of particles. So alpha decay, alpha particle, that's that helium-4, 2. So it doesn't matter what your starting isotope is or what you end up with. You can make up one like I did earlier. Go, okay, Q, 10, 20, and then see what happens when it goes through alpha decay. Similar here, make up an element, Q, 10, 20, have it go through beta plus decay. Okay, I've got 0 plus 1. So what am I going to get from this? I don't care what this other thing is, all right? Let's say this is element squiggly. Doesn't matter. We want to know what's the change, what's going on here. You're going to find that primarily from whatever's happening in the middle part. So, do know what these names mean from this context, but you don't have to be able to pick it out the other way around, like I mentioned, getting. Remember, gamma decay is pure energy. That's just gamma rays. It's at the far end of the electromagnetic spectrum. So that's going to be something you'll want to consider there. There's a bunch of different combinations of ones those can make. I guess another thing that might be important to mention is that with these decays, we're particularly looking at um, the nucleus. So electrons don't live in the nucleus. So we're not going to talk about those. Technically, the electrons get removed later or added later. But again, we're looking at like the immediate change. The change to the nucleus is what we're interested in. And because I won't make you use or won't let you use the periodic table, don't worry about any of these from the end. Again, I hope you would be able to do this and then use, like if you were in class, the chart that we showed or the periodic table from just Google or something during a quiz or for studying, not during the test. Um, but like I said, during the exam, not going to make you have to do any of those. Okay, I hope that helps. Good luck, and hopefully it's not too bad.